Chapter 4 talks about reactions that take place in solutions. And one of the best measurements of the solution that we're working with is units of concentration. Units of concentration tell us how much solute is dissolved in our solvent. In this class, for you guys, mostly it's going to be water. And this is a quantitative measurement, so it's how much, not exactly what is it. And it relies on the fact that the number of moles of the solute stays the same. And I should actually say calculations we're going to do later in this video rely on that factor. But everything harkens back to the moles of substance dissolved in our solvent. So molarity is the most common unit of concentration you're going to see. That is symbolized by a capital M, right, where molarity is moles of solute divided by liters of solvent. Right, so molarity, so then you can write this as moles per liter. Or just the capital M means moles per liter. Right, so we can take that or out from the middle, we can take that or out from the middle, we can just throw an equal sign in there. And then we can also say that it's equal, symbol-wise, to N over V, number of moles over the volume. So, molality is a unit that you're going to run into in a general chemistry 2 type course. Molality, is the moles of solute. So it's symbolized by a lowercase m. It's moles of solute per kilogram of solvent. Right. Parts per million is a unit, actually I'll talk about parts per million and parts per billion together. These two units are very common in environmental studies and things like that. You know, levels of toxins that are acceptable before they get out of hand, relative abundance of things in the environment. These are common units with that, and it's very helpful to be able to convert between normal units of concentration, i.e. molarity, and parts per million. So parts per million is equal to, and it's ppm, I wrote it right there. ppm is equal to mgs per liter. Right, so milligrams per liter, and then ppb, parts per billion, is equal to micrograms per liter. Right, where milligrams, right, 1 milligram equals 1 times 10 to the negative third grams, and 1 microgram equals 1 times 10 to the negative 6 grams. On to the next topic, we have dilutions. Dilution calculations are specifically helpful in the lab setting when you have stock solutions that are made up that are often the most concentrated form of a particular substance. If you're in kind of an introductory chemistry lab, your solutions will likely be made for you. If you're in a higher level lab later in college or in high school, let's say you're in an analytical lab in college, or let's say you're in an AP lab in high school, and you may need to make your own solutions, dilution equations are very, very helpful. And these rely on the fact that the number of moles remains constant in a dilution, right? So remember, we're adding more solvent to our solute-solvent system, so we're just increasing the amount of solvent, but the amount of solute stays the same, right? So when we increase the amount of solvent, the relative amount of solute to solvent ratio goes down. Okay. So let's do the practice problem. So let's say we're in a lab. We have an 8 molar stock solution of sodium hydroxide. We're doing an experiment that requires us to use 75 mils of 0.5 molar sodium hydroxide. So we need to dilute our stock solution, right? Now, you can work these problems forwards and or backwards. You know, you can go one way or the other. In this case, we have our final volume, so we know what our final volume is going to be. Okay, we know what our final concentration is going to be, and we have our initial concentration, right? So we say a lot that M1V1 equals N2V2. That's to say that your initial molarity times your initial volume of stock solution or more concentrated solution is equal to the final molarity times the final volume, or the volume of your diluted solution times the molarity of your diluted solution. You can really you can designate either species as M1 or M2 as long as you stay consistent. Also, there's no specific units you necessarily need to use with this particular equation. As long as they're the same on both sides, you're good to go. So if you're going between parts per million and molarity, you cannot do that with this equation. You need to convert either parts per million or molarity or parts per million. But you can go from molarity to molarity, molality to molality, parts per million, parts per million, parts per billion, parts per billion. That's fine. And then volume units need to be the same on both sides as well. But it's not, there's no rule that it has to be in liters, or, that it has to be in moles, or excuse me, that it has to be in molarity or molality. You can use, you're going to get moles eventually. That's to say. But you're going to run into problems like this, where you just kind of do the best you can with what you have, and it always works out. So there's no specific units as long as you stay consistent. So let's just do the practice problem. We have 8 molar NaOH. We need to find 75 mils of 0.5 molar. So we know that M1V1 equals M2V2. Let's zoom in on that. Right? Our M1 is 8.00 molar times an unknown volume. M2 is 0.500 molar. V2 is 75 mils. Right? And what you're going to do is you're just going to solve. So we're going to divide both sides by 8. Sorry. Right? So these cancel out. Right? So we're left with volume in units of milliliters. We are good. And if you crunch the numbers on this, and it's literally just multiply and then divide, so 0.5 times 75 divided by 8, you need, so V1 equals 4.6875 mils. I would say that's about 4.69 to 4.70 mils. If we really wanted to go to 4 sig figs, we could. We really should go to 3, so it should be 4.69 milliliters. That's really all there is to these equations. You'll find some practice problems on the next page that's going to serve for good review for the part of the quiz. But yeah, as far as this, I am done. See you in part 2.